Okay. Hello. Hello. Good afternoon, Sylvia. All right. Sylvia is like the most I gotta say, it is, and hello. I am aware, Sylvia, that you totally get here so superly on time. That's all I can say. I'm not saying you're the only one, but I'm just saying it is definitely knows. Whoa, there's a real actual Catherine. Oh, yes, I remember you. Okay. Yes. Yes. Hello. Hello. Okay. This is awesome. Okay. Well, everybody's bringing it together. Hold on. Okay. Hey, oh, I haven't said hello to, okay. Hold on. Sorry. So good afternoon, Sylvie. Good afternoon, Catherine. And goodbye, Catherine. Okay. Hello, Marina. Hello, Jake. Hello. Oh, she's back. Okay. Hello. Is that a person? Okay. Hello, Abigail. Hey, Ashton. Hi, Devon. Hello, Kayla. Hello, Giselle. Hey, Ashley. Okay. Wait. There's someone else. Wait, is that what the? That's hello, Giselle. Yes, I see you. Okay, that is an interloper. That is a 204. Yes. Hello. Why she looks so upset? Because she misses this class. Okay. Yes. Hello. I didn't know you guys were friends. Okay. Uh, okay. All right. We actually have a lot to do. I have a lot of ground to cover with you. Today's our last class. We're all very aware of that. It's always been a long class. It's always an exhausting class at the end of the day. We all know that too. But there's a lot of issues. Okay, so this is always a tricky point in the year for me. Let me. So here's the deal. There's two things happening. There's two frontiers always, but particularly at this point in the year. There's academics and there's intellectual. Like there's the outcomes and there's the ideas. This is a point in the year where what always happens is that I know that your largest concern is your grades. Well, that for many of you, a very large concern right now at this point in the semester is how things are all going to turn out, particularly with regard to your grades. I totally get that. I totally respect that. That should be, I mean, what else? Of course, you are concerned with your grades. I know that, and I'm going to address that in a second in more ways than one. Let me just also tell you that this is the point in the year where usually I'm much more confident of your grades than you are for most of you, especially any of you who is still with me at this point, any of you who is still standing in the course and still here listening at 4:30 on the very last week. If you're here with me at all right now, it's extraordinarily likely that I feel very confident about how things are going to wind up for you within reason. And you might not feel so confident, especially because there's still some crucial grading information that I still owe a lot of you. That is to say, a lot of you still have not gotten your midterm exam back. I'm very aware of that, and very pained by that for you. You will get it back, but not in very much time to help you do anything about the final exam. I'm very aware of that. I wanted to a number of things. Let me address about that before we get into material substance. First of all, as long as you did the midterm exam, as long as you didn't leave huge areas blank, as long as you turned it in when you were supposed to, and you put both your feet forward on it, then it will come out. There will be a grade on it, and it probably worked out a lot better than you might think. And you've done your hard job already. Like the ball has been in my court for a while and still is in my court, but you did your hard job with the midterm. And I want to tell you right now that the final that you will have, that we have to have, that we're going to talk about, the final is not meant at all to be as stressful or as long or as taxing or as heavy in your mind as the midterm was. What I want to make clear right now before we go any further is, especially because I am aware that many of you won't really be able to use the benefits of your midterm to help you with your final. And I know that can be stressful and frustrating, and I apologize for it. I want to make it clear again that I know that, and I know that's a thing. So for that reason, plus many other reasons that are always true, you should go into your final thinking that what it is an opportunity to cushion or to protect, help you just in case things didn't work out the way you would have liked on the midterm. That is to say, as it says in Google Classroom, but I want to make this very clear to everybody again, because I know this is a stressful time of the semester for everybody. And some of my habits or some of my pacing does not make it any less stressful for people. If it turns out that you did fine on the midterm, which I'm sure a lot of you actually did, if you did fine on the midterm and you got a good grade, and you filled out most of it and you just made some errors here or there, then the final is not going to ruin your average. If you did fine on the midterm and you did well on the midterm, and if it turns out you did better on the midterm than you do on the final, the midterm will count a lot more heavily in your average. If on the other hand, it turns out, especially if it turns out like too late for you to do anything about it, that your midterm didn't go so well, but you do okay on the final, which will be shorter and less stressful and all of that, then the final will count for you a lot more heavily in your average. I know I said this in Google Classroom. This is one of many things I want to say right now as we end the semester. I want to make it clear that whichever the two tests you do better on for each of you will count more heavily in your average than the other. I'm totally throwing away the other, but it'll count whichever one is. Sorry. So I have a lot more to say about this, but let me just start by that. So you should look at the final as an opportunity to help your grade. It won't hurt your grade if you did fine on the midterm. There's more to say, but wait, Fatima, sorry, you have a question? Or do you?
Yeah, sorry. I do have a question.
Oh, yeah.
What if you still haven't gotten your midterm grade back?
Well, that's what I'm saying. No, I'm addressing you still will, but I'm saying that some of you have not. I'm aware of that, and I'm apologizing. And if you haven't, it doesn't reflect anything about you. It has to do with where you are in the alphabet or something like that. I just, for some reason this year, I had all of the exams at the same time, which was dumb on my part. I don't know how that happened. And for some reason, all of them were super long, and I've just been plodding through them like one a day or something. Like, I'm getting older. For some reason, they've been going super slowly. So some of you still have not gotten back, including you. That is not personal to you. But what I'm saying right now is to address that I know that makes your life frustrating. So I'm trying to say a couple of things right now to reassure you that your life should still work out okay. So number one, so let me even back up further. I'm still continuing to work on them. You'll get them back. They will count in your grade if they help you. They'll count less if they don't help you, because I know you don't have time to adjust to that surprise if it's a surprise. I also want to say that once this class is over, or in the next couple of weeks when we're doing all this, and any one of you, I mean, I'm trying to tell you all that I think your grades are going to work out better than you think, especially because I know that I've created this hardship. But any one of you, say Fatima or anybody else, who at any moment is like individually concerned, like, okay, yes, Yaverbam, you're making all these big speeches, that's fine. But like, I need to know what's going on. Like I need to know what's going on. If you reach out to me personally by text or by email, I will address things with you right there. Like sometimes people send me an email and I just say right away, okay, like people will say, yeah, that's all fine, Yaverbam, but like, actually I'm trying to transfer, or I'm trying to graduate, or like, I really need this information right now. And often what I'll do is say, okay, fine, got you. And then I come back to them 15 minutes later with it's finished. Like I put them to the top of the pile and I'm finished grading theirs. And then I can correspond with them, or you, or whoever it is, about the exact particularities of your grade. That is number one. Like Fatima or anybody else, I'm not trying to leave anybody else in the dark. Number two, I can tell you all that any of you, if I think at all that you're in jeopardy of an F or a D or something like that, or even probably like a C minus, if I have any reason to believe that any one of you is like actually gunning for something really problematic like that, I would have already reached out to you, or I will reach out to you, and I will say, hold on, we do actually have a situation here. What can we do about this? Or I do need you to rock the final. Please know this going in. Like as I get this information, I will reach out to you if I think there's a concern. And if you think there's a concern, then you reach out to me. In general, what I'm trying to tell you all, to the extent that you can believe me, is if you're not hearing anything on an individual level like that, and you've been doing fine in lab, and you've been doing homeworks and stuff and just like basically being here, then that doesn't guarantee you an A. I'm not saying you're guaranteed an A, but I'm saying your grade is probably in the A or B range. It's probably not a crisis. At the least, it's not a crisis. And you will be learning more over the next 2 weeks. I'm just trying to tell everybody, I know the information is coming later than it should. So just know that I know that. And I won't shock anybody on CUNY first with a failing grade or something like that. If I haven't said this before, let me make this very clear right now. If in the worst case scenario, and again, I just feel like you should all know this for a variety of reasons. In the worst case scenario, let's say it's the night before all the grades are due to CUNY first, and I'm looking now at your final exam and your midterm or whatever, and it turns out for whatever you really bombed both or something. It turns out like you did them both, but you did really badly. Wait, let me back up also and say for a second, like if you know in your heart that you literally didn't do something, that's very big. Like if you never took the midterm or you left huge parts of it blank, or you leave huge parts of the final blank or don't do it, that's a different thing. Like then you know that there's an issue and you should be reaching out to me or something. But assuming that you, right, then like that's different. But if you've done everything, if you've done what you were supposed to do and you tried your best, if the night before grades are due, if I see, oh my God, just use Fatima as an example. If I see, oh my God, Fatima's been like a good student. I thought she was fine. I thought everything was fine. Like I had a midterm from hers that took me a long time to grade. I have this final from hers, but oh my God, like she actually totally got everything wrong on the final and she got everything wrong on the midterm. And even though I'm doing my best to try like see the best in her, like, oh, this is a real situation. If I see the night before the grades are due to CUNY first, that someone's like literally going to get a D in this class or an F in this class, and I didn't realize it before, and they didn't realize it, and I didn't give them adequate warning to do something about it, in that worst case scenario, if that happens, what I'm telling you right now, what I will do is put an incomplete on your transcript, which is not really what they're supposed to be for, but that's what I use them for, and someday I'll get in trouble for it. I use incomplete to mean I have an incomplete understanding of this situation, or we have an incomplete situation here. If any of you, I'm telling you right now, if you see an incomplete on your transcript, what that means is please reach out to me. Something is unresolved here. Something is unresolved, and you, the student, and I did not somehow have time to resolve this before the crisis. So I'm giving you an incomplete so that you come to me and say politely, okay, I see an incomplete. What's the story? Like, what can we, and I will look and I will say, this is what we need to do so that you don't have a D or an F in this class or a C minus. C minus is like borderline, but I know for you guys, even a C minus is something you don't want to be surprised by. I know that. Occasionally C minuses can come surprisingly, but definitely D's or F's. You won't get one out of nowhere. You'll get an incomplete, and that will mean that you have an opportunity, as long as you reach out and contact me and say politely, what can we do? We will figure out the situation, because I don't believe in people just being shocked irrevocably on CUNY first by a situation that they didn't have a chance to rectify. Okay, so so first of all, let me just stop right there with that, because that's an unusual policy. I know, in fact, it's like not what we're supposed to do, but that is what I do. And I will tell you that every semester in all of my classes, I usually do that. Usually happens like at least once or twice to one or two students. I end up giving them an incomplete, even though they weren't in the hospital or anything. And I will also tell you that of the one or two students that I do, that happens every semester, usually one immediately responds to me and says, what is this? Like, you said to reach out to you, tell me what to do. And then we talk and then we work it out and then they do fine. And usually the other one never reaches out to me, which really shows, oh, okay, they really did ghost the whole class. Like, it's not just my incomplete understanding. Like, they ghosted the whole class so much they didn't even hear my speech on the last day. They don't even know what this is. And then that incomplete does turn into a WU or whatever the policy is, right? So it's my way of reaching out and saying, hold on, if you're still with me, I'm still with you. But if you've left me a long time ago, then you left me a long time ago. Not me, but the course. So first of all, let me just pause. So this is my long way of saying I am not perfect. I am far behind. I'm taking far longer on these grades than I ever should have. And I know it causes stress. So I want to tell you the millions of ways that I'm here to try to assure you that I'm aware of that. And at the end, you should not be stressed. As long as you're doing what you're supposed to be doing, even if you don't have a perfect understanding of all the physics details, if you don't hear from me and you don't reach out to me and there's no real crisis, then there won't be a crisis. And the incomplete is the final stopgap, is my final stopgap on that whole thing. Is if there's something really fell through the cracks, we have one last chance to catch it. Oh, and I should make clear, if you've never gotten an incomplete before, by the way, what incomplete means is just that. It means that there's a period of time and that extends into the next semester where the professor, I mean, it's meant for people that were in the hospital. That's who then therefore couldn't take the final exam because they were in the hospital or something. That's what it's meant for. But the point of it is that if you get an incomplete, it just, then your grade is just in pause until the professor and the student work out and do whatever they need to do and resubmit the final exam or whatever. And then the professor submits a grade like a B- or a B or whatever, or an A or whatever it is. And then the grade takes over the incomplete, and the incomplete is like it never happened. It doesn't do anything to your average. It doesn't become a permanent blot on your transcript. It never ends up on your transcript. The grade ends up on your transcript. So it's just like a holding pattern on a grade that's meant for medical emergencies, but I use it to be like, whoa, wait a second. Something went on here that we both missed. Let's catch it before. Okay, so let me pause on that for a second. First of all, is everything I'm saying, can you raise your hand electronically if you get the larger message that I'm, thank you. Okay, thank you. Thank you. Okay, cool. Okay, thank you. All right. And again, I know I'm over talking this. The reason I'm over talking this now is I want to get all these grading issues sort of out of the way now because it is our last class. I want to end the class by giving you the final chapter of physics. Like I want this class to end on a physics note. Again, I want the class to end on an intellectual note. Surely, yes, I want it to end on me giving you whatever material that, yes, you're in some form going to give back to me in the final exam. But I want to front load all of this by addressing all the academic concerns that I can right now, given all of the fact that we're all human beings. I want to spend this time right now addressing all the academic stress so that hopefully, within about an hour or so, whatever last hour I'm talking about physics, what I want you all to do for the last hour of the class and for the last week after this is, as best as you possibly can, trust yourself and trust me that you've already done the hard work for this class. It's not going to get any harder. It shouldn't get any more stressful. You're over the hump. The ball is in my court. And what I want more than anything is for you guys to trust yourselves and relax enough and trust me so that you can actually absorb the physics point of this class. My real objective is to have you appreciate and understand some physics on your way out, and just make the most honorable demonstration you can toward learning that. So we're going to talk still more about grades for a few more minutes so that the goal, and again, remember the other qualification here is that if nothing I'm saying right now, like satisfies you in terms of grades or calms you down, again, I can understand that. Because if I were in your position, my primary concern would be grades too. I get that. Like, you're not here for the love of physics. I deep in my heart, I fantasize I want to convert you into loving physics, but I know that's not why you're here in the first place. You're here to do a job and get the job done and know that your job was appropriately and fairly recognized. It will be. It will be. But if nothing I say convinces you or satisfies you, then please reach out when we're done over the next week or whatever. Text me or email me, and we will talk until we both feel better about the situation. One other version of that I keep forgetting is, like, what can you still hand in things to me? Like, is it too late for you still to get some points if you're concerned? No, it's not too late. Like, what you might be noticing is that a lot of old points for participation and homeworks are starting to land back on your plate now. Like, I'm going through all the old stuff and trying to get everything organized including your midterms, and get it all back to you. You may notice that a lot of old points are coming back. Now, similarly, if I'm doing that for you, you can do that for me. If you still want to turn in another revision on some old homework, or there's some homework that you never did, yes, I will take them. I will take them up until the last day of classes, which is next Tuesday. For the next week, if you are concerned about points and you see opportunities to get more points and you want to turn them in, sure, by all means, especially many of those game portals, like days you showed video or something like that, you can do all that. The only thing I don't want, and you'll even notice, some of you might even notice that some homeworks that some of you, if you did a draft on a homework or you did a second draft, and you got points and then you got more points. At this point, I've been going back, and anybody that turned in a couple of drafts on a homework and really showed they tried and they got better and they tried again, even if the homework is still not perfect, you might have noticed, some of you, that at this point, if you turned in a couple of drafts on a homework, at this point, I gave you all the points for it. We're just like, it's like amnesty period or whatever. You've done your due diligence. Now I'm giving you credit for your due diligence. And so we're all catching up with each other. So you can still turn in things if you want. One thing I'd recommend, if you're very concerned about your grade, or just very concerned that I talk so much during the Zoom and other people do that you've never really gotten a chance to shine in the Zoom or something like that, there is a portal that some of you noticed and some of you might not. There's one game portal called Your Best. It's just and it's worth some number of points. That is exactly as it sounds. Whatever you think was your best work so far, whether it was graded or not, if you have some homework that you did do well on, that you did get a lot of points, you got more, and you know that I think it was good, you can reprint that homework, or you could take that same copy of the homework, even if it was already graded, and put it in the portal called Your Best. Or if you've got something that I never saw, like you take really good notes in the class. And for example, if you take really good notes in the class, and you feel like you've really been engaged, but there's no way I could have known that to this point or something, put some copy of a bunch of your notes in the Your Best portal. Any and all of you, or if you did get your midterm back, or when you do, if you did well on it, put it in the portal. Whatever you think was like your finest day, or one of your finer days, or a finer representation of you at your finest, put it in the portal. Because another thing I'm just trying to say with all of this, and it's been true from the beginning, and it's true no matter what, is that an average is one number that's supposed to represent a whole bunch of varying numbers. We all have to do averages in school and in life. We all have to reduce each one of you to an average because that's the practical thing to do. You've done all these different things of all these different numbers. We reduce you to one for simplicity's sake, but there's 1,000 million different ways to take an average. There's 1,000 million ways to do a grading system. As long as it's a system and it treats everybody with the same rules, then it's fair. And mine does. I treat you all with the same rules, but I'm a believer that my system has to treat you all the same, but it doesn't have to evaluate you each at your middle. There's all different kinds of averages in the world. I see no reason that you should be represented by your most blah vanilla day in this class any more than would it be fair for me to put a grade on your transcript that represented your worst day in the class. I don't want to be judged by my worst, and I don't want to judge you by your worst or even your middle. I would rather make a judgment, have a numerical system that renders a judgment on each of you based on you at your best. And that's all of you. And all of your bests have different flavors. So one thing you absolutely can do to help me help you do that is wherever you think your best work was, put it in that portal called Your Best. It will give you some points, and it'll serve as a reminder to me of really who you are in this course at your best. And if your grade at the end is like right on a borderline, or if I have to make a judgment call, that will help me a lot. Make the judgment call. Okay, wait, sorry, there's things that I know I'm babbling way too much. Soon we will get off this topic, but I want to make it clear that from here on out, on the one hand, there's still things you can do to ensure that you all get as good a grade as possible. But I'm also kind of saying that from here on in, you also don't have to worry about it that much. Like from here on in, whatever time we have left, I'd rather actually think about physics rather than grades. But wait, I'm looking in the chat. Oh, thank you. Oh, okay. Okay, one person said something very nice in the chat. Thank you very much. I appreciate it. But someone, and tell me if so the absolute last day. to submit anything from behind, like old homeworks or extra credit or any of those game things. Truly the last day is Tuesday, the 16th. That's the last day. Sorry.
The 17th.
Or I'm sorry, Tuesday today's
17th.
but wait, why isn't Wednesday the 17th? Wait, am I confused? Isn't Wednesday the 17th?
Wednesday's the 17th.
And
Never mind, my bad.
Oh, okay. But that's fine. That's fine. And if I got, but yeah, so Tuesday, the 16th is the last day for you to submit back stuff to me if you want. One thing again, I'm going to ask, the one thing I don't really want is a whole bunch of back game turns, like the daily game 5-point reflection. It's a little silly to submit a whole bunch of those at this point. It's silly, it's sort of inefficient, it's sort of disingenuous because they're meant to be daily reflections, and it's not worth it because each one of them is only worth 5 points. Like, don't spend your time doing that. Anything else I'll take. Back homeworks, back revisions, I will. Those, it's a little silly and it sort of clogs the system. But anything else I will by Tuesday the 16th. On that note, I almost forgot. Did I answer? Wait, was that Kate? Was whoever asked that? Maybe put in direct chat if I actually answered it, or if the answer is clear. Okay, great, thank you. Okay, another thing. Now the final. I will address the final more substantively, like once I get into the physics of today. But the logistics of the final, I think I posted in Google Classroom. It'll be a document that's sort of like the one that you did yesterday, Monday, in the lab that you practice in the lab. Of course, I'm going to address that document. I'll tell you right now, I know that document's really messy and really hard to read. I'll address that too. Ideally, I would make a whole new document, but as you can see, things are very clogged for some reason on my end this semester. So I can't guarantee that I'm going to make a whole new document, but I can tell you, your document will be shorter than that by a long shot. It will be shorter than that. My grading of it will be very lenient. Like, your goal, whatever I give you as the final, your goal is to fill the whole thing out. Your goal is to just not overlook things or leave big blank spaces. That's your primary goal, is to put your best foot forward and show that you've confronted the material. But the final will be a shorter version of what you saw in the lab on Monday. I will address it in a few minutes, but it'll be posted no later than 8 p.m. Thursday of next week. Again, this is in Google Classroom. I'm just saying this now to be clear, but it's in Google Classroom. That'll be posted no later than Thursday, the 18th. It'll be due back to me Monday, the 22nd. The one thing in all this that I do have to be strict about, about getting your documents back. Like, no homework's no later than the 16th, and the final has to come in no later than the 22nd. You can see what a hard time I've had for whatever reason, like being on with the midterms. So I'm going to get like 100 finals that are all due to be turned around, within a very, very short period of time. So I can't take the final late. That's the one thing that would be a problem. So it's posted Thursday night, no later than 8 p.m. Thursday night, the 18th. It'll be due no later than midnight of Monday, the 22nd. Let me pause. It'll be shorter than what you practiced yesterday, but it'll be similar in nature to what you practiced yesterday. Again, we're going to soon address it substantively when I stop yammering about this. But let me pause for a second and just ask. And I see there's things in the chat. But let me pause for a second and ask. Is the basic logistics, the logistical expectations of the final exam, is that clear? Could you put up your electronic hand if the final exam logistics are clear? That's 1, 2, 3, okay, 4, 5, okay, 6, 7. Oh, even a party hat. Okay, cool. I appreciate it. Okay, now I'm just going to pause again. I know this is all, and in this part of the year, I always sound so stressed and so frenetic, but I promise you, I sound stressed because I'm stressed for you. Like, because and if you're not, then I don't want to add to your stress. It'll work out fine. I just want to talk about physics, but I know I've put people in a position, and I know it's that time of year. But okay, I'm looking in the chat. Okay. Wait. 1 second. Okay. Okay. I'm just looking at the direct chat. I feel like, wait, did I just? Yes. Okay. And if you are sending me things in direct chat, that's fine. And just let me know if my response is clarifying. And again, you can all either any of you can contact me privately and we can look at things. I don't mean well, I do mean privately. Yeah. Okay. I think that's wait, is that okay. Okay. So let me pause again. So far, we're going to shift gears in a second. We're going to shift a couple of gears, but any questions at all about like the overall? And let me also again be clarified of it here in science. I mean, just to be blunt, okay. When I say someone's fine, if I say I think you're going to be fine with your grades, or I think you shouldn't worry. I mean, let me just be very clear what I mean by that. It doesn't mean I'm guaranteeing every one of you an A. I mean, a lot of you will get in the A's or A minuses. A lot of you will. And again, I don't have a limit to how many A minuses or A's there could be. On the one hand, let me say that. I am saying that. There's not a distribution maximum or something. I'm perfectly happy if a ton of you get A minuses or A's. And many of you will. But I'm not guaranteeing that, and especially people that have done a lot of work. I'm not guaranteeing that you're all getting A's. What I'm saying realistically, to be blunt, is that unless there's like a real issue, like something's really missing and you know it or I know it, then I am saying that when I say you're fine, it's going to be fine. Many of you might get something in the B's. Like, I don't want to mislead you. I consider a B fine. I don't want to shock you either. So if you're the kind of person that's like, oh, well, this is all very well and good, but a B is not good enough for me. I need to know whether I'm getting an A. I can respect that. And then maybe you want to reach out to me personally, like if you're still worried, like, because you don't know I respect that for a lot of people, a B is not fine. I will say on a sidebar, if you're doing science, you really should start getting used to B's and you should start not worrying about them because a B in science is fine and the whole world knows that, but that's whatever. I'm saying to you, some of you will get B's or B minuses. And I wouldn't like, I'm not necessarily reaching out to someone in advance and saying, I know that's going to happen. Like that could happen because of the final or whatever. Some of you will get B or B minuses and I consider that fine. But I am saying like for any of you to get anything lower than a B minus, something's probably missing somewhere, and either you should know that or I should know it and you should have heard from me or something like that. That's okay. I don't want to be, I'm not saying no one's going to get B's or B minuses. And if you're really worried about that, you should talk to me personally. But I am saying, I know that nobody wants a C or a D or an F. I don't know if that helped. I don't know if that clarified anything, but okay, we're going to go on in a second. Okay. Yeah. Yeah, okay, wait, I'm just responding to something in the text. And also, all of you, don't forget that lab plays a huge role in this as well in the grades. Okay. Any other questions? I was just answering things in the chat. Any other questions about this? Again, we're going to shift gears in a moment. Okay.
I have a
Oh,
question.
sorry. Yeah.
So I see that for the gain turns that you posted for us to fill out for extra credit. So I see that there's like two different sections, one that is due every class and one that actually doesn't have like a deadline, but it seems like you post it all together in one day. It says January 25th. Like there's a one that has a title like game really, really, really wrong. Or like there's another one that's like game 11.
Right.
So what's the difference between two? Because I did all the games that were due on that day of the lecture, but not the ones that has the title like, oh, really, really, really wrong or
Right.
etc.
Right. Great question. I totally know what you mean. Yeah. Okay. And you've been doing the right thing. Yes. So all of the ones that are all due that same day at the end, all of those ones with funny titles, like you're saying, like
Yes.
really, really wrong. Yeah. All of those, first of all, you totally could still do. Though all of those are due at any time you want when applicable. So like absolutely, like the really, really wrong one is for any day that you actually said something wrong. Like, so it's more easy for you if you do remember which day it was, or you remember what you said or whatever. I mean, that might be tricky for you to remember, but if you, any of those, you could totally still hand in over the next few days, over the next week. Oh, sorry, hold on. Those, or like the one that says, or like show video, like you're showing video today. And I know for a fact you have shown video like a million times. Like, and I don't have a record of exactly every single time, but I know it was like a million times. So if you, even that, if you in good faith, especially if you happen to have screenshots or anything, but if you went back and said, like, I showed video on this day and this day and this day, like I know you did. So yes, you can still hand in those kinds of things. That's what they're meant for any special thing that you did. Anytime you want, you could indicate that totally all of those, or like the YouTube, if you've ever looked at a YouTube video from this class or subscribed or whatever, you could tell me that now and it totally counts. So does that mean the only ones I don't want to get now are those daily turn, the 5-point ones, right? Which also I know you've done. I mean, right. So does that make sense? Does that answer?
Yeah, it makes sense now. Like I just wanted to make sure like ones that we can still hand in and ones that we shouldn't, basically, because it was already due on the days that we had lecture. Just wanted to clarify which ones, okay.
Right.
All right, thank you.
Thank you. Awesome. Okay, wait, there's something in the chat. Okay, great. But this is good. Again, I'm glad if anybody's any other questions like this, not that you can't ask them for the rest of the class, but okay. So we're gonna do another gear shift now. There's gonna be a couple more beats. Oh, well, okay, here's a question in the chat. There's a question in the direct. Wait, no, that's fine. No, this is what today's for. So there's another question in the direct chat. I'm gonna answer to everybody. I'll try to say it concisely. All that game stuff, folks, technically speaking, all of the game stuff is optional. It is. In fact, honestly, folks, even the actual homework, which is worth a lot more points than a lot of the games, but all that stuff is technically optional in the sense that you get no deductions for not turning them in. You don't get zeros in your average for not turning them in. All of that game stuff, all the homework stuff is all extra points that help your average. But when you don't do them, they don't hurt your average. And I know I've said this before, and I won't over talk it, but someone just asked that in the direct chat. It's a fair question. I mean, my grading system is unusual, but the reason it's worth addressing right now, not only for that person, but for all of you, is this is another way of saying, I will accept back homeworks over the next week from you. Yes, I will. And I will accept the things that you just asked for. It's the least I could do since I'm still sending stuff back to you guys. But I don't want to confuse you. For many of you, it's not worth it. I'm not saying you have to. Don't be afraid. Don't go back now and think of it as a checklist where you have to now give me all the things you never gave me before. That's not the case. All of those are points and opportunities to help you if you're worried about your grade, or if like if you did terrible on the midterm, and again, even if some of you don't know your number, like you know whether you filled it all out or not. Like I'm saying, if you know in your heart that you left the whole thing blank, or you turned it in 3 days late with no explanation or something, okay, then you probably do need a lot of points to help cushion your situation. Then you would want to, but no, all of these homework things, they're all lot. I know I've said this before, but the whole system is designed so that you could get an A or a B, either by doing really well on exams and labs, or by doing a ton of homework and a ton of participation and labs. It's designed so that there's more than one road to an A or a B, but nobody has to do all the roads. So yes, they're all optional. And if you feel like you have a high enough cushion in your lab numbers or the exam numbers, if you know, then don't worry about it this week. Worry about other classes. Okay. So, no. Oh, okay. So someone thought, hello. So yeah. Don't worry about zero. That's why this person's good to see you. Good to see you. Okay, no, I'm glad. So again, little questions like this, I promise you, even though I know some of you were thinking like, okay, he said that before or something. It's that time of year where it's that time of year. So if there's anything still that's not clear about the grading system, or you're like, your heart rate is up to here, just text me or email me personally. And even if it takes me a few hours or something, like we'll rediscuss it. It's okay. Well, someone is here that no, this is okay. Okay, that's interesting. Okay, pardon me for a second. So we're going to pause for a second. If there's other questions like that, ask them. Otherwise, we're going to shift gears again. Hold on. I'm just. Okay. Wait. Oh, Fatima. You see, okay, that's Fatima. That the other name on that freaked me out for a second. I was like, well,
Oh, sorry. There's something wrong with my Zoom and I'm having to use my friends. The picture is gonna stay. I sincerely apologize.
no, that's totally fine. But I'm glad you clarified, because I swear in all of this talk, the number of times when I'm saying like, as long as you're here and you're with me,
Yeah.
and I was like, oh my God, someone just joined this class on the last day. Like, how is that person going to get a good grade? Okay.
Yeah.
Okay. Fine. All good. Okay. All right. So I think we're going to move on in a second. So now my goal, okay. I'm going to turn on my board now. Okay. So let's get to the material. Now, my job today, as far as I can, my goal is to put together the material for you finally, to show you what this material has been about, mostly. And I would like you to take notes for sure. Like, I'm not saying this is going to be a joke. I do feel like I have a lot to say. I would like you to take notes. I would like you to try to follow what I'm going to say. And yes, ultimately, then I'm going to relate it back to the exam. But the best way to listen to everything I'm going to try to say, and you should participate too. I'm not saying that, but the best way to try to listen to what I'm going to try to say today is for you to see how the different pieces of this class actually fit together. Not only that the pieces connect, all the different motions that you did one lab after another, the whole idea of this class is that each motion that you prove to be true or false in each lab, and each little subtopic that match to it in lecture, that each of these subtopics actually go in a sequence for a reason. And the sequence is like the sequence of a proof or a derivation or an argument, like whether it's a science argument or a math derivation, or like a court of law case, which is partly why we call them motions, because this is a college of criminal justice, right? The idea is that we've been building a case all this semester. And each little subtopic we did, and each little conclusion that we came to in each little subtopic is meant to be the next plank in a longer argument that's ultimately reaching a conclusion. And we want you to see the conclusion by the end of this course. And so whenever I'm talking about anything right now, try to, what your goal is to see if you follow me, to see if you follow the narrative. Don't just try to understand the individual items. Don't just try to understand the individual trees. See if you can see the forest. That's our primary goal for all of you. And as an overarching thing, that's what the final exam was meant to be designed to get you to see. I mean, I guess I'll say this as a side road. The reason you had we had these fragmented, weird, like statements that are like flying this way and flying that way. That wasn't an accident of old Xeroxing. I mean, it's regrettable, but it wasn't an accident. And the reason that all the questions are labeled like X and T and F, like all jumbled up like that is what we're trying. We know that when science comes to us in the first place, to many of us, including me and the person I wrote the exam with, at first, science seems like a bunch of just jumbled facts and jumbled math problems that like we have to just navigate. At first, it feels that way, or when you're navigating your way through a lab and there's just like jumbled equipment everywhere, whatever. What we want to when we walk you through that final, what we're trying to have you have is the experience of evaluating a bunch of facts, but then stepping back and putting them together in an order and seeing that the order leads somewhere. That's what we were. So the idea behind the exam is that first you say whether this thing is true, whether that thing is true, whether that thing is false, just like you did in the lab. Then you're supposed to go back and solve the math problems, as I know you tried on Monday. Then you're supposed to go back and reach a concise English conclusion about each of those little math problems. And then you're supposed to put them all together and see the argument. That's supposed to be the idea of that exam. However, I do recognize that having those facts like all cockeyed like that all over the place on the page and having you go through in layers like that, I realize now these days that is more confusing than it needs to be. I recognize that. And the Xerox is so bad at this point. The Xerox is so hideous that adds another layer of just annoyance that I fully recognize. I am not promising that I'll be able to fix all that in time for you for next Thursday. I'm going to try. I am going to try. But I am promising once again that I know that, and there will be huge benefit of the doubt when I'm looking at your exams and the difficulty that causes. But what I want you guys to do is try to focus on the big picture of all this. And what's the big picture? Okay, let me start. The big picture is plank number one. The big picture is this. Okay. Point number one of today, I'm telling you this now, I'm saying, in 1806, a man named Thomas Young, a British physicist, was very technically skilled. He wasn't a major theoretician. He didn't come up with like a new idea. He didn't pose a new question. He had incredibly advanced technical, experimental, laboratory skill. He was so skilled that he was able in 1806 to create a super thin column of light. He focused a beam of light down to a very, very, very tight, thin column, thin beam, so that then this beam of light came in and was able to hit a barrier and pass through two tiny, tiny, thin nearby slits in the barrier, and thereby start traveling from the barrier to the other side of the lab in two twin, two nearby twin, i.e. identical, super thin beams of light that went across the lab and eventually hit a screen on the other side of the lab. Let me say that again more slowly or a different way. Thomas Young was able to do with light what eventually, about a century later, we were able to do with a technology called lasers. Okay, eventually, lasers were developed in the 20th century, and a laser is an incredibly, incredibly thin, tight beam of light, and so thin and so tight that that a laser can create light of all very, very, very much one common color and all light with one common property. A laser beam is like a very, very pure beam of light. Now that technology came along in the early 20th century after we'd already developed incandescent light bulbs like Thomas Edison and all that. But Thomas Young, in the early 1800s, but way before there were lasers and before there were even light bulbs, he took light sometimes from the sun, from outside, and sometimes from a candle. And he was able to set up lenses in front of the candle or lenses, near a window, and arrange the lenses so precisely and so carefully that he could focus the light into a tiny, tiny controlled beam. And this tiny controlled beam then came to a barrier, an opaque barrier, and went through two tiny slits in the barrier and went across the lab to the other side to a screen. So Thomas Young was able technologically, or developed the technology, okay, what I'm trying to say is that Thomas Young sent two identical beams of light through two nearby slits and the two beams of light emerged from these two slits, hit a screen on the other side. And what Thomas Young saw on the other side was alternating bands of light and dark, light, dark, light, dark. And he found that those alternating bands of light and dark followed or demonstrated that equation that you established in your simulation in the lab, a week and 2 days ago. He found, in other words, that the light pattern that emerged on the screen on the other side worked just the same way as a pattern of water on the other side of two slits in a barrier through which water is traveling. It all makes perfect. And again, let me say, just like you already knew the theory of water last week, and now I'm telling you that this experiment happened with light in 1806, like you already understand. I mean, I think I learned last week from you. I think you already understood that we make water waves pass through those two slits in a barrier. In your case, it was a computer simulation, but you watch crests and troughs of water going through two barriers. The crests and the troughs interfere with each other as the water's traveling across. And so that what you get on the other side is you get this interference pattern, right? You get some places on the other side where waves are really high, some places where they're really low. And specifically low is the interesting part. You get these alternating regions of high water activity and low water activity, high water activity, low water activity. And very specifically, like you get places on the other side where a lot of water's coming in from one slit and a lot of water's coming in from the other slit, but you find a place on the other side where the water seems to be really low, right? And that's not a surprise at all. You're not like, wait, how did water plus water make low water? You're not surprised at all because you're taking it for granted already, or you're used to the idea that water is waving. So that on the other side, since there's all these crests and all these troughs, at a lot of places on the other side of your water tank, or your simulated ripple tank, you'll have places where a crest of water waves from one slit meets a trough from water waves from the other slit, and a crest and a trough meet each other, cancel each other out, and you get no water activity at all, right? In other words, with water, you can have a lot of places where water plus water seems to yield no water. And it's not just a temporary effect. If the whole point of that equation is that as long as you pick a point where the length that the water had to travel from one slit is exactly 1/2 wavelength longer than the length that the water had to travel from the other slit, or 3 wavelengths longer, or 5 wavelengths longer, or 7 wavelengths longer, as long as this path is an odd number of wavelengths longer than that path, then no matter how long you look, when a crest comes from this slit, necessarily a trough is coming from the other slit, right? Because a wavelength means the distance from one crest to the next crest. A wavelength is a full cycle. So from one crest to the next crest is a full wavelength. From one crest to a trough is a half wavelength. Oh, exactly. Okay, I see something in the chat. Yes. Yes, I'm going to agree with that in 1 second. What I'm saying is, as long as we all understand that a crest is always a full wavelength away from the next crest, and it's 2 wavelengths away from the next crest, and it's 3 wavelengths away from the next crest. Similarly, the crests and troughs come in multiples of half wavelengths. So as long as you're looking at a spot that is an odd number of half wavelengths away, as long as you're looking at a spot for which the path from one slit is an odd number of half wavelengths away farther than the path from the other slit, then that spot that you're looking at always has what somebody has just put in the chat, always experiences what's called destructive interference. If it's a crest coming in from this guy, then it'll be a trough coming in from that guy. If later on it's a trough coming in from here, then it'll be a crest coming in from here. Some spots, in other words, there's a whole bunch of spots. This is what the equation's supposed to mean. And again, I'm giving you big picture now. I'm not asking you to solve any problems right now. I'm just asking you to stay tuned with me on this, the big picture. I'm saying the big picture of that equation is an equation that tells you at what spots you'll always have destructive interference, and at what spots you'll always have constructive interference. That equation is saying as long as it says delta L, that's like the difference in lengths. It's saying as long as the difference in length from one slit is a certain number of half wavelengths larger than the distance, the length from the other slit, then you're looking at a spot that's always going to have destructive interference. In other words, and I'm going to pause for a second to make sure everybody understands me. I'm saying with water, as you simulated 2 weeks ago, with water, you can send water through one slit and water continuously through the other slit. And if you look on the other side, you'll get this interference pattern where in a lot of places there's permanent, huge activity of the water, huge crest, like constructive interference, like water going up and down all the time. And other places, they'll be quiet all the time. Like even though water's coming in, you see regions where it seems like the water's just flat all the time. Those are called nodes or nodal lines. And they happen because water travels in waves and the waves can interfere with one another. In other words, again, to go back to the beginning of the semester, two particles cannot be in the same place at the same time, but two waves can be in the same place at the same time. And when two waves are in the same place at the same time, we call that interference, and it can be either constructive and make them bigger or destructive and make them smaller. So water plus water can make no water and can do so permanently in an interference pattern like you saw 2 weeks ago. The point I'm making right now, and then I'm going to pause and look to see if what I'm saying right now is with anything that you know to be waves, you can predict spots where you'll have permanently it seems stuff plus stuff yields no stuff because you're getting permanent destructive interference. Waves can interfere with each other. Only waves can interfere with each other. Particles cannot. Baseball plus baseball never makes no baseball. Baseball plus baseball makes collision. Baseballs bounce off each other. I'm going to pause for a second. So far, are you with, something's in the chat. Oh, I think that was a destructive interference thing. Yeah, okay. Wait, just raise your hand if you're so far understand my point. Kind of, sort of. Okay. So, okay, cool. I believe you, sort of. Okay, so you knew that about what, like you did the details, the mathematical details of the water last week, but the larger picture, I think you understood because you're like, yeah, water's a wave. It can do this. What I'm saying now is everybody, just like you, people in the world understood that waves could do that. They knew it for centuries. And they knew for centuries in this whole debate about the nature of light, they knew that if light could ever demonstrate that feature, then that would be very strong, if not definitive evidence that light was a wave. Just nobody could get light down. Nobody could control light to the degree sufficient to create a situation like this. But in 1806, Thomas Young came along and said, I think I can do it. So he didn't have a new idea, but he had a new demonstration. And Thomas Young, okay, I'll just say the sentence and then Jake. So what I'm just saying right now is that as of 1806 or 1804, I mean, he did it more than once, right as of the turn of the 19th century, Thomas Young in England finally got light to demonstrate an interference. And I'm not forgetting Jake, I'll just say this. Thomas Young sent light through two slits, and on the other end of the apparatus, on a screen on the other side of the lab, he got light bands of light, dark, light, dark, light, dark, which today you can do very easily through thin films and through what are called oh my God, I always forget what they're called. How come I'm forgetting this? But it's easy to do today with lasers and small, because we have lasers today. We have light bulbs and lasers. But the first time it was done was 1806. And the point is this, that he shined two lights. He shone lights through two slits. And whereas on the other side, it should have just been a whole bunch of light, there were all these places on the other side of the apparatus where light from one slit plus light from the other slit was yielding darkness. I mean, it's really that simple. Qualitatively, the fact that he got a bunch of bands of darkness only makes sense if light is acting like a wave, or more specifically, and then I'll get Jake, more specifically, he found that the bands of light and darkness fit that pattern and the equation that you got last week. And he showed, okay, here are the places where we're getting destructive interference, where we're getting darkness permanently, and those dark bands are right at the places where the path from one slit is longer than the path from the other slit by a half wavelength. So what Thomas Young said is, look, this would not happen if light were made of little particles called light particles. If light were made of tiny, tiny things like baseballs, you could never have a bit of light from here plus a bit from light from there making darkness. So light must be traveling as a wave, is what we inferred from the Thomas Young two-slit interference experiment of 1806. The point is, light did then and continues to do today in apparatuses like that. Light demonstrates the same property that water waves do, which is constructive and destructive interference according to that equation. Okay, that's what I'm saying right now. But sorry, Jake, go.
I'm sorry, I just had my hand up from before. I didn't have anything to add.
All right, sorry. Okay. 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 So far again, I'm saying, and then I'm going to stop again and see if people are with me. Saying right now, so this was the purpose. So I'm all, by the way, I should make this clear too. The way I'm talking today, I'm going to talk backwards, kind of. I'm sort of trying to give you your most recent punchlines or conclusions and tell you what they mean to try to put the whole course together in perspective. So I'm kind of starting almost at the end right here, kind of. But right now what I'm saying is, the reason you did an interference pattern thing with water last week was to put you in the same mindset as people had been for a couple of centuries before someone finally did it with light. What I'm saying now is the fact that light produces that equation, or produces results described by that equation, seems to indicate that light travels as a wave, which again means, now to go back to our course, it means that light travels the same way sound does. It means that light is not a thing. I mean, according to this, light is not a thing unto itself. Light is a phenomenon. Light is an activity. Light is a behavior of a collection of things, right? Please bear in mind from here on in, whenever I say wave in any context, or if your exam says wave in any context, what I honestly think you should really picture whenever we say waves, you could picture water waves. I mean, that was, that's common, and that's what you did in your simulation last week. But honestly, when anybody from here on in life or in science ever says waves, I think the best thing to picture or consider in your mind is sound waves, which we spent a lot of time talking about with the Doppler effect and all of that. Please remember, sound, which I think we all believe in sound. It's very, very real. It's kind of concrete, like we experience sound all the time. We know what we mean by sound. But please remember, whenever we say sound, sound is very, very much an example of this larger idea of waves in that, and I know I've said this a million times, but I just want to drum it in. The idea behind sound is that when I send a sound from my mouth to your ears, something certainly must be moving for there to be a trip taken by sound from my mouth to your ears. There's certainly a motion. Motion certainly follows the laws of physics. Okay, what's moving? When I send a sound from my mouth to your ears, forgetting about the internet, like assuming we were in the same room together right now, if I send a sound from my mouth to your ears, what we believe is moving is a whole bunch of air molecules. There's air between me and you. We believe that air molecules are moving according to very, very precise laws of physics. But the laws of physics, according to which the air molecules are moving, are the laws of simple harmonic oscillation and all those cosines and everything that we spent all this time doing at the beginning of the semester. That is, yes, when I talk to you, air is moving, but how is air moving? What we believe is that there's a whole collection of air molecules between you and me, and we believe that some air molecules over here are oscillating back and forth cosinusoidally, and then air molecules over here are oscillating harmonically back and forth with a certain angular frequency and all that, cosinusoidally. Like air molecules are acting like a bunch of little masses on springs, and air molecules are acting like a little bunch of masses on springs, and so a whole set of air molecules are all oscillating in their little neighborhoods, and these air molecules, and they're all oscillating the same way, but all out of phase with one another by a constant step. So at the end of the day, what we think when we say air molecules are moving such that sound goes from me to you, what we mean by that is a bunch of air molecules are moving back and forth in place. And a bunch are moving back and forth in place, and a bunch are moving back and forth in place. What we mean very specifically is that there is no air molecule that is actually going from my mouth to your ears. I know I've said it a million times. By the way, if you think you've heard me say this 27 times already in the course, then I've got two things to say. Number one, you're one of the people that's probably getting a good grade. If you've heard me say this 27 times already and you're verging on boredom and you think you get it good, that means you're with me. Number two, if you think you've heard me say it 27 times, probably I've actually said it 54, and I'm going to say it 56 more times, because the point is that the air between you and me is a medium of material particles, each of which is oscillating cosinusoidally, such that on the whole, some immaterial pulse can thereby propagate from my mouth to your ears. Like, again, let me remind you that all the air molecules that are oscillating harmonically, they together constitute the medium. The medium is the material particles that oscillate harmonically in time and in space, so that something immaterial then can propagate through that medium. Bottom line, if you're really following everything I'm saying, and you've been following it all semester, you'll understand what I mean, and you'll believe me when I say there's no such thing as a sound particle, right? Sound is not a thing. No matter how precise our microscopes are, no matter how closely we look at that air between you and me, we're never going to find a piece of sound. We're just going to find pieces of air, and air is not sound. Right? You could have air sitting still and be very quiet. Air is not sound. Air is required for sound. If I take the air away, if I take the medium away, then there's no sound. Sound cannot exist without the medium. The medium is the material collection of particles that oscillate in such a precise way that then this phenomenon, this immaterial entity effect, can pass through the medium from one point in space to another. So the first premise of the whole thing is waves are not material. Waves are wiggles through wiggling pieces of material. Now we are saying, wait, you're with me, right? Like, just raise your hand, electronic hand, if you're with me so far. I know I've said it, right, okay, cool. And I know I've said it a million times. But now what we're saying is, okay, we have reason to believe now that light is like sound. Light, apparently, if it goes through two slit interference, light is like sound. Light is not a thing, according to what we know in this context. Light, no matter how closely you look at it, you're never going to find a little bit of light. You're just okay. You're just going to find little bits of something that are wiggling to allow for the light to pass through. Pause, Eugen. I'm sorry. Or was that from your? Or is that? Okay, cool. No, it just means you're paying. Okay, all right. Okay, in like totally stupid terms right now, what I'm saying is anytime we ever conceive of a wave motion like sound, we necessarily have to conceive of a medium. And I'm going to say it one more time because this eluded me for years, frankly. Like, please remember that the medium so air is the medium for sound, but air is not just, it's not just something that the sound is passing through. Like I used to think when people talk about sound passing through air, I thought the air was some kind of sort of like obstacle that the sound was passing through. Kind of like if I swim, I'm swimming through water and like I have to push the water away to get through the water and the water's kind of in my way. And if the water's like really thick or if it was like jello, it would slow me down or something like that. That's not like analogous to what sound is experiencing when sound goes through the medium. The medium has to be there for sound to get through, right? I know I keep saying it, but I can't say it enough. The air is not in the way of the sound. The air is what makes the sound possible. And literally, it's not just that. And when I say this, when I say for a wave to propagate, there must be a medium, please understand, that is not me saying that scientists have always noticed that waves always seem to come with media, so that scientists have a hard time predicting that they would ever find a wave without a medium. It's not just that. It's not just that we always seem to observe waves to go through media. If what we're saying is we can't even conceive of the logic of what it would even mean to talk about a wave without a medium. A wave is a wiggle. So if there's a wiggle, something's got to be wiggling. That's the medium. Okay. Like I'm just like trying to nail that down. It's by definition, you cannot have wave propagation unless there is some oscillate. In fact, that's the best way for me to put it. I've actually never said it that way before. What I'm saying is we cannot conceive of propagation without first conceiving of of collective oscillation, okay? For a ripple and a crest and a trough to pass along an x-axis, there must be a bunch of things oscillating up and down along the y-axis. Okay. I'm going to pause right there. Wait, am I going to pause right? I'm going to pause right there for a second. I have to make a so that's 2 beats. I have to make a left turn. Okay. Oh, what just happened? One second. Oh, yeah. Hold on. Sorry. Okay. I'm saying if something is a wiggle, there must be something wiggling. I'm saying there's no such thing as a wave without a medium. I'm also saying apparently light is a wave. So I'm asking now, I'm not asking you, I'm asking rhetorically, I'm asking myself, history asked itself, what is the medium for light? What is it? Like, again, remember, with sound, the medium is generally air. I mean, it could also be like water or a guitar string or something like that, but generally, the medium for sound is air. So much so that, as one of you once pointed out in the class, if I went to outer space where there is no air, right? Like in outer space, there's no sound because there's no air. It's that straightforward. It doesn't matter what you do. You could create all the vibrations you think you want, but if there's nothing there to vibrate, then there ain't no sound. Well, so what is it that's vibrating, that's oscillating? What collection of particles or things or entities is vibrating to allow for light? And this is a rhetorical question that I'm going to answer. But now I think Jake does wait. Okay. Were you going to answer it? Or?
I was just going to ask, what's the word before? It says oscillating in something to allow for the
Oh,
propagation.
sorry. Right. Absolutely. It says in order. Sorry. Good point. Sorry. Okay.
Thank you.
Thank you. Thank you. Okay. Okay, so this is a question that is going to take me a little while to answer now, but it's a very important question. What is the medium for light? Like, what if light is not a thing? if it's a phenomenon, a behavior of a bunch of things, what are the things? And whatever they are, they must be pretty fundamental, because if they're right, again, like, you know, for sound to exist, there's got to be this fundamental sort of ever-present thing already there called air for there to be sound. I mean, you know, it's a pretty common basic thing. So what is it that's fundamental enough to allow for the passage of light? Let me remind you, like we see stars. We see stars. So what? Well, if we see stars, that means the light from stars is coming from stars to us. So somehow light is traveling through outer space to our eyes. Now, sound does not travel through outer space, but apparently light does. So whatever the thing is that's wiggling to make for light, apparently it's out there in outer space where nothing else is. That's a little mysterious. Like, it ain't air. It's even more fundamental than air, whatever it is. So what is it? Good question. I'm going to say, hold that thought. Like, we're going to look at another bit of material in the course, another thing that seems sort of fragmented or disassociated, perhaps. Like, I've got this thought in my mind of what the heck could be the medium for light if light is wiggling. Well, let's shift gears. Okay, 6 o'clock. Let's shift gears and look at another bit of the course and see if we can hook it up with this. Oh, but we have to take a small break first. I am going to give you, I know it's a long class, I am going to give you a small break. I have to give you a twofold break. I almost always forget this. I apologize. Something that we do need to do that does matter, that I always feel awkward about, but it does matter, and I would like to do, which is the student evaluations of faculty. I'm going to put in the, so I'm going to pause for a second. What I'm going to ask you to do is take a few minutes. I'm going to put the link in the chat. Maybe some of you have already done it, maybe because you saw that I put it in the chat, in the Google stream, maybe, or maybe you did it during another class. But if you have not, I'm going to ask you where to go. Yes, here it goes. I'm going to ask you to pause for a second, go to the link that's in the chat. Please fill out the student evaluation. Obviously, be honest, be thorough. I hope you know at this point in your career, they truly, truly are anonymous. I can tell you, in fact, that I've been on the committee for years that designs and oversees these things. And I can tell you two things. One, even though I'm on the committee, we have no idea who wrote what about whom, I promise you. I don't even know if you do one or not. I don't know. I'm asking you to do them because number two, as awkward as I find it, or, you know, nervous making as I find it, I can tell you they do matter. This is your moment where you actually have more power over the school than you might think. They actually are taken far more seriously. They don't always feel that way. You don't always get, you know, that doesn't always feel that way. But I promise you that if you fill these things out, whatever you say, as long as you're honest and thorough, even if they don't affect your future at the school, they will affect the future of your upcoming, like, brothers and sisters. They really do matter. So I'm going to ask, so you don't have to do it, of course, but I really do have to give you time to make the choice to do it. So I'm going to say, please, for a moment, go to this link, fill out the class evaluation on this class. And then when you've done it, feel free to take like a 5-minute break or so. Like, we still have a bunch to cover here, but then take a 5-minute break to your discretion. And once you've done that, then please put up your electronic hand just to say that you're done or that you're ready to move on. Again, I won't know. If you choose not to do it, that's your business. I won't know who did it and who did not, I promise. But I would like you to let me know once you're ready for me to move on. So do the evaluation, please. Then take a 5-minute break. Then put up your electronic hand and then just keep it up. And then we'll resume this material. Oh, our hands up because, some of you have already done it. Is that the point? Or, oh, great. Oh, that's awesome. Okay. But still give yourself a 5-minute break then. But okay, that's awesome. Okay. So, okay. And I'm going to.
I actually had a question, Professor.
Sorry. Yeah. Sorry.
How do you want us to break up lecture and recitation, since we kind of do it all as one thing?
Yeah. It's all the same thing. Right. I know this is a funny technicality. Right. It's all one thing. There's no distinction. But ideally, you actually would fill out a form for each one. It could be the identical answers for both. Ideally, all time is accounted for. I mean, you have me for 3 hours of your life. So like that should be recorded somewhere. So ideally you'd fill out a form for a lecture, a form for rec, and you could say the exact same things in both, or or something like that. Or if you want to just be much more fast on one of them, that's fine. But yeah, there's no distinction as far as, and by the way, you can make that as a critique if you want, like, but right, they're both the same thing. But they're both hours of your life that you spend with me. So yes, good point.
Okay.
Okay, thank you. Okay, so I will shut up, and again, take your time, everybody, and then, but once you're ready, really? Well, there's something in the journal. Huh. Awesome, thank you. Awesome. Thank you. Okay. Okay. I appreciate that you guys are doing this very much. Just keep your hands up if you're done. And I'm not rushing anybody. But pretty soon I might start, even if you're still working when I start, then just keep doing it and ignore me for a minute, but or put another way, I guess, maybe send me a direct chat if you want a little more time. I just want to make sure that I'm not waiting for people who are like actually out of the room or something. But so in a few minutes, but keep your hands up if you are done, please. Thank you. And we'll take a few more minutes. Okay. I think we should, so if you're still working on it, please do. But I'm gonna start gently here, because we do want to, because because I have to start. So you could so thank you for putting your hands up. Okay, I'm gonna put my board back. Again, I'm not trying to rush any, well. Okay, here comes the board back. Yeah, so you can put your hands down. If you're still working, please do. You'll catch up with this in a second. Don't let me bother you, but. Okay. And you could put your hand, so I'm going to start. You could put your hands down if you want. Okay, thank you. All right. So let's go to this other part of the course that we've been doing for weeks. It seems to have nothing to do with anything, but remember this whole business of electrostatic fields and field line diagrams. Okay, remember, I can't emphasize enough, remember, to say that there's field over here in space is to say that there's information over here in space describing the vital statistics of what's going on over here in space. More specifically, if there's field, so field lines, field is unthingy things. Field is just information. If there's field lines over here, that means that the information describing the location, the magnitude, and the distribution of charge or mass over here. I'm going to say that one more time. If there's field lines over here in space, that means that's what's over here is not things, but information. Describing, information, capturing, conveying, describing the location, magnitude, and distribution of some thingy things, i.e. charge or mass over here. Field lines in space are the information of stuff that's somewhere else in space. And the way that field lines capture, sorry. Okay. The way that field lines convey, the way field lines over here convey the presence of and the shape and the location of charge or mass over there is through asymmetry. Field lines, as it says at the bottom of the board, and you can put your hands down, please. Maybe I'll put, okay. Just putting the hand, okay. I mean, unless you're asking a question, but okay. What this says on the board over here is that the way field lines convey information is through asymmetry. What I mean by that, like it says at the bottom of the board, is that a field line pattern, a pattern of field lines, is only as asymmetric as their source, as that which creates the field lines. So for example, if you have a point of charge somewhere in space creating field, a point is zero dimensional. Therefore, it has what I would call zero-dimensional asymmetry. It is asymmetric in no dimensions. A point does not in any way prefer or mark out or label or distinguish any one dimension of space any more than any other dimension. So the field lines from a point spread out equally in all dimensions. No field line puts any special attention or distinguishing properties on any one dimension of space when the field lines are caused by a point. If, however, you had, say, a plate of charge, well, let's go down to the bottom. If you had a line of charge, if you had a bunch of protons next to each other, all in a line, all jam-packed together in a long static line of charge, right? Each little proton, each little bit of charge would cause field lines that radiate out equally symmetrically in all directions. Let's say you had a proton right here creating field lines in all directions, and then another proton right next to it. Oh, there goes my board, creating field lines in all directions. I'll just finish this point and I'll get the board again. Then this point here would create field lines. For example, one going up and to the right, but the dot next to it would cause a field line going up and to the left. So the left component would cancel out with the right component, and you would just be left with two vertical components. Field lines are the vector sum of all of the magnitudes and directions causing them, right? So what I'm saying at the end of the day, let me put the board back. What I'm saying at the end of the day is that if you had a whole bunch of dots next to each other forming a line, at the end of the day, the field lines from that charge line, if you had a line of charge, like a bunch of protons in a wire, the field lines would radiate out in all directions from that line. The field lines from a line would create what you might call, would fall into a pattern that you might call spokes, like spokes of a wheel. In other words, the field lines from a line of charge would be like legs from a caterpillar. They would go out in all directions except one. What one? The one direction or the one axis along which the charge was lying. Right? So the field lines that from a line would demonstrate what you might call one-dimensional asymmetry. They're symmetric in all dimensions except for one, the one of the one axis along which charge has been placed, right? So that field line picture would tell space, hey, space, there's a bunch of charge along a line here, along the x-axis. How does space know that there's a bunch of charge along an x-axis? Because there's no field lines pointing along that line, right? That's where all the field lines are emanating from. So, and last example, like if you had a plate of charge, if you had a bunch of charge filling up two dimensions of space along an x-axis and a y-axis, the field lines would come out just along the z-axis, so to speak. So space would know, because there's only field lines along the z-axis, space would know, so to speak, that there was charge along the other two. A plate has two-dimensional asymmetry. We're placing charge along two dimensions of space. We're marking out two dimensions of space as sort of special or different because they have charge all that. Therefore, two dimensions of space would not get field lines. Field lines, so it's like a figure ground kind of thing. Field lines convey what's going on in space by how asymmetric they are. The asymmetries in the field lines show asymmetries in space occupied by mass or charge. Now, why am I saying all this? Because and the converse of what I'm saying is that field lines are always as simple as they possibly can be. Given the pattern of field lines is always as simple and it's symmetric and smooth as it can possibly be, given the shape, the distribution of the source that creates those field lines. So what if we hike up our analysis one level in complexity? What if instead of having a line, and again, if you take anything away from what I'm saying right now, take away that a line of static charge would create spokes going out in all directions. If I were walking through space and I saw spokes of field lines, I would know that there was a line of charge at the central axis from which all those spokes emanated, radiated. Okay, but what if I don't have a line of charge? What if I go into the lab and I create a flowing line of charge? What if I put a bunch of protons next to each other all in a line, but I have those protons or electrons continuously moving in one direction? In other words, what if I have a current going through a wire? a current continuously flowing through a wire. So, you know, as part of some large closed circuit, like you were playing with in the lab, and I'm looking at one branch of that circuit, and I see there's continuously charge steadily flowing through that wire. So here's a situation that's fairly simple, but it's one step more complex than any situation we've looked at so far. Like here's a situation kind of like in early physics, in Physics 101, where we now have a change, but a constant change. We've got charges moving, but they're always moving and always moving at the same rate. And if I just keep looking at any point in the wire, I always see the same number of charges flowing through. That's the same number of coulombs flowing past a point every second. We call that an ampere. We call that steady current, right? What if I have steady current? What kind of field situation does that create? Well, remember, field line diagrams are only as simple, are always as simple as they can be. They're only as complicated or asymmetric as that which caused them. So this fairly simple situation of constant flow should create some kind of fairly simple field line picture. Well, it can't be as simple as spokes, because spokes are what come out from a static line. Spokes are what come out of a line of charge that's just sitting there. If I put a line of charge there, I'll get spokes coming out of it. But imagine the line is continuously moving forward. So each one of these spokes is continuously moving forward, like this spoke, like each charge is carrying with it its whole burst of radiating field lines. They're continually moving. So all of these bursts are going to fall into some new pattern. It's not going to be the same pattern because they're all moving, but it's got to be a pattern, much like when you stood in lab 3 and you had your long string and your partner had the other end of the long string, and you're shaking the string up and down. So you're sending all these crests and troughs back and forth along the string. Like at first it's very complicated, like bump, bump, bump going across, bump, bump, bump coming back. But after a while, if you keep sending these bumps and troughs going back and forth, eventually they fall into a new pattern, which looked like this, right? Like it's still a pattern, but it's a different pattern. There's variations in it, but it's a steady set of variations. So what does that look like when we do that with field lines? Well, with moving charges, the field lines from moving charges are as simple as they can be, but no simpler. They've got to be field lines that show that there's a line, but that the line has direction. I'm going to switch screens for a minute and show you what it looks like. You would have, if I gave you enough time to think of this, you would eventually come up with it because it's the only choice, but it might take you a little while. I'm just going to switch screens and show you. Oh, did I just lose it? Hold on one second. Sorry. Here we go. Okay, hold on. Here it comes. Yes. It looks like this. If you have steady flow going from a steady flow of current, I, it creates a bunch of field lines that fall into a simple pattern. So they fall into a simple pattern and get farther and farther, less and less dense as they get farther and farther away from the source, as field lines are supposed to do. They are as symmetric as they can possibly be, but they show space what's happening. They have one-dimensional asymmetry in that they are radiating, they are going out in all directions equally, except for the direction that the charge is along. They're not spreading out from that direction, because they would do that if the line were steady. They're dynamically spreading out from that direction. So they swirl around the current. As this diagram is showing, if the current is going to the right, each line is, if the current is going to the right in the manner of my thumb, then each line swirls forward in the manner of my fingers. If the current goes to the left, then the field lines go the other way. Again, notice this picture is very different from the other picture. It's a different pattern because now we have charges moving rather than charges sitting still. So something fundamentally different is happening. So the picture is fundamentally different in a way, but it has all the same properties of the other picture. It's capturing the information of the source. This picture is the simplest possible way, the most symmetric way to indicate to space something is happening along this line, and the thing that's happening along this line has direction. Remember it, right? So this is that picture. This is the field line picture from a moving bunch of charges. This is the field line picture we get if a bunch of electric field lines are in motion or are changing. This picture is the field line picture that results if you're getting steadily changing fields. This picture is called a magnetic field line diagram. Okay, I'm going to say it one more time. I'm going to switch back to the other board in a second. Well, yes, I'm going to switch back to the other board. Hold on one second. Okay, I see. Oh, someone's here. And I'm starting to get concerned about time. Okay, Jake, question.
So you had, what's the difference, I guess, between B and I?
Oh, great question. And actually easier to answer than many questions. So I stands for current. I is the flow of charges that's causing this field. B stands for the field lines themselves. These field, so these field lines that come from moving charges, or in other words, these field lines that come from a bunch of electric fields that are changing continually, these field lines are called magnetic field lines. And for some strange reason, the letter that we use to stand for magnetism is not M, but rather B. I mean, there is a reason, it's not worth going into, but so B stands for the field lines. I stands for the thing that caused them. This is analogous to saying Q stands for a point charge. It causes E field lines. In fact, let me write that right now. A point Q causes E field lines to radiate from it. A flow I causes B field lines to loop around it. So first of all, does that answer? I mean, did that answer you?
Yeah, that answers that question. Thank you.
Okay, no, thank you. Okay, so now, and I'm watching the time, folks. Believe me, and I know this all again sounds like what's he even doing? Maybe nothing. But the point I just want to like nail down right now to everybody is points of charge cause electrical field lines to radiate out from a point of charge causes electrostatic field lines to radiate out from it. A line of charge, by the way, would cause electrical field lines to spoke out of it. Static charge causes field lines to emanate from static charge. But once you put the charge in motion, in effect, what you're doing is you're putting the field lines in motion. You're causing the field lines to change constantly. Let me rephrase that again. If you put a bunch of charge in constant motion, like in a constant flow, like a steady current, right? This is like constant velocity from physics 101. If you put a bunch of charges in a steady flow, they are all moving, but they're all moving in the same way. So if you were to, it's like a river, right? If you were to stand here and stare at it, at any given moment, what you're staring at is a different charge, but you're always staring at one charge, right? It's a steady flow. So all the lines that were emanating out from this flow steadily rearrange them. They rearrange themselves into a new pattern. They're constantly moving. They create a whole new thing, but they do fall into a pattern. They fall into the simplest possible pattern that has all the that spreads out equally in all space, that indicates that they are the source. They fall into a pattern just that's as simple and follows all the rules of the original pattern that was originally caused by just a line of charge. Only it's a new pattern because this is a new situation. So what is the pattern? So I'm saying a point causes things to radiate out from it. A line causes things, field lines to spoke out of it. But a line of flow causes field lines to loop around it. We actually call those field lines magnetic field lines. This is what magnetism is. Magnetism is caused by moving charges. Electricity is caused by charges. Magnetism is caused by currents. Now that's in itself, that's interesting. We could spend a whole course on magnets if we wanted to, but actually for our purposes right now, I don't even care. Like that's just a word for, like magnetism is just the word for the field picture that arises once we set the electric field picture into a steady flow. The key thing to take away from what I'm saying right now, everybody, the key thing to take away from what I'm saying right now, with 25 minutes left in the class, with 25 minutes left in the semester, the key thing to take away from what I'm saying right now is that in the same symmetric manner that a dot causes field lines to radiate out symmetrically from it, a flow, an arrow, causes field lines to loop symmetrically around it. Really, there's no other thing that could, if there was going to be field lines that were going to be created from a flow, if you really think it through, you realize there's no other picture that the lines could have obeyed. There's no simpler picture that is possible that could convey the idea of a line with a certain direction. The way space knows that there's a flow down here going that way is a bunch of lines looping around it, circling around it in a certain orientation. Now, why am I saying this? What does this have to do with anything? Well, I want to go one step more and then stop. What if we go one step more? What if now that flow flows? What if we have current that's getting faster and faster as it goes? I'm not going to do this forever. I'm just going one step more. But you see what I started with, a line of charge and it created field lines. Then I made that line of charge have direction or velocity, so it created these loops around it. What if we go one step further? Oh, I just lost the board. And I probably just lost. What if we go one step further and imagine that first we had a line of charge sitting there, like physics 101, constant position. Then we considered a line of charge flowing, so like physics 101, constant velocity, right? And we said what we get is loops around it. What if we go one step further and consider like acceleration? What if the current has some value that gets bigger, gets bigger and bigger as time moves on? What if the charges are moving faster and faster? What will we get then? Well, presumably follow the same logic. When the line was sitting there, it caused loops around it. Now we have loops around that line. If the loops now are undergoing a continuous increase or change, the only next logical, most simple possible symmetric thing that can happen is we will find like, in other words, if charge is flowing, if there's a flow, it creates B field lines looping around the flow. But if now the lines themselves are flowing, if now there's an increase, then we'll get lines looping around the old loops, right? So we have this, we get this. If the current's increasing, now each one of these loops will get a field line around it, right? Because we just created another level of flow. Okay, I'm going to say this quickly. I'm watching the time. Yeah, and I'm saying a lot. I know you don't have to absorb every single detail. Just try to get the big picture of what I'm saying. I'm saying field lines are always as simple as the situation that creates them. Every time we hike up the situation, every time we make the source of field lines one level more complex, then the field lines get one level more complex. They're always an interplay of symmetry and asymmetry. So if we had a flowing line, if we had a flowing line of charge, i.e. a current, it creates field lines that loop around it. If the current is not steady, if the current starts changing, then these lines themselves have flow now, right? They're not steady anymore. They're changing. Like if this thing gets stronger, each one of them would get stronger. So now each one of them is like a flow unto itself. So it would create, so each one of these loops around a line would create a loop around it. You get loop and then a loop around it. Now, if you made a current that was co-sinusoidal, if you had a current that was going back and forth in value forever, right? then this process could continue indefinitely. You could get a change, in current, which makes, a current would make a magnetic field line. But if the current was changing, then the magnetic field line would be changing. So it would create a line around it. But if it changed back, then that'd be a new change. If it's going up and down, then this change would create, just like on a cosine graph, you have rises and runs, but the rises and runs have rises and runs, and the rises, there's slope, there's concavity, and it goes on and on forever, right? So you could make, if you make a current that's cosinusoidal in nature, if the current is harmonically oscillating perpetually in time, then it can make a field line, which makes a field line, which makes a field line, which makes a field line, and eventually you get electric or magnetic, whatever you want to say, you get field lines which would wiggle back and forth and oscillate back and forth and eventually propagate out in the manner of a wave. If you set up, in other words, field lines are the information created by the presence of charges. If you set the charges in motion, you get looping field lines. If you set the motion in motion, the loops create loops. If you arrange things properly so that you have charge that is in harmonic oscillation, or current that's in harmonic oscillation, you're going to get field lines which oscillate next to field lines, which oscillate next to field lines, which oscillate next to field lines, honestly. And eventually these field lines propagate out in space in the manner of a wave, okay? And remember, for any, and eventually, in other words, you get field lines that obey that equation. That we studied in the first half of the semester. You could say it's the electric field lines, you could say it's the magnetic field lines. But remember, for any wave, right? Remember, like for any wave, the speed of the wave, the speed of propagation equals the angular frequency over the angular wave number, right? Well, it turns out if you create an electrical situation that is cosinusoidal in time, it creates fields, which create fields, which create fields, which create fields, which propagate away, which fly away, field lines fly away in the manner of a wave, and they fly away at a speed that is omega over k, and it turns out with E and B fields oscillating in this manner, the speed of the wave turns out to be the speed of light. This is what light is. Now I've got 15 more minutes. First thing I'm saying right here is, I'm saying this is the medium for light. I'm saying when light waves travel through space, what's wiggling, what's rippling is electric and magnetic fields. Fields are oscillating harmonically back and forth in a collection that allows for the propagation of what we perceive as, or we understand to be light. The propagation, we know this in part because the speed at which this happens is the speed of light. So put another way, what I'm saying is every time, if there's a charge over here, then space over here knows it, because the charge over here creates field lines that go out and land everywhere, including over here. When this charge moves, or this charge gets bigger and joins another charge, or something like that, it creates updates to the field. It sends out new information, informational updates, new field lines. It sends ripples through the old field line. Like the new field lines have to adjust to the change. The ripple that goes through the field lines, the pulse that propagates through these field lines propagates at the speed of light. What light is updates and ripples. It's updates to and ripples through fields, electric and magnetic fields. What light is a wiggle or set of wiggles or set of oscillations in electrostatic and magnetostatic fields. What light is updates in the information of space over here describing what's happening over there. Light is how different parts of space send messages to other parts of space. I'm ultimately saying that light is a wiggle, and all wiggles have to be caused by things wiggling. But the things that wiggle to cause light to travel, the things that are wiggling here are not air molecules, are not water molecules. They are electric field vectors or electric field lines. What are electric field lines? They are not thingy things. They are bits of raw information sitting in space. So waves, like sound, are pulses of information that we believe are possible because bits of material are vibrating back and forth to send the pulses of information through. Like, again, remember, sound is possible. Sound goes from my mouth to your ears because a bunch of air molecules oscillate in such an organized pattern that they can allow the sound to go from my mouth to your ears. We can believe in the non-material existence of sound because we believe it comes about due to the material existence of a bunch of air molecules. Light now, and similarly, we can believe in the non-material idea of electric fields because we see material things such as protons and electrons responding and accelerating to the forces generated by these non-material entities known as electric fields. But now what I'm saying at the end of the day is when a non-material entity known as a field oscillates in a certain cosinusoidal way, it creates a non-material pulse through it. The non-material pulse through the non-material medium called electric fields is known as light. That's what light is. That's point number one. I think that's a fairly huge point. But point number two, that's point whatever it is, that's four. Final point of the whole course is okay, light consists of ripples, pulses propagating through the field lines that exist everywhere in space. Again, I'm saying the medium for light is electric fields. But I'm saying you should really take seriously, but a bizarre idea that it's a real idea. It's true. I'm not like joking, but it's a very heavy idea because, again, please remember, I'm saying light is an immaterial pulse through a medium. But now I'm also saying for the first time in this class, the medium itself is immaterial. Light is ripples through information. That's what light is. And it can happen anywhere in space because there's electricity and magnetism everywhere in space. Because as long as you put one proton anywhere in the universe, it creates electrical field lines everywhere in the universe. So light can travel through empty space. When light waves propagate from a star to us on Earth, we find, oh wait, and sorry, it's okay, we still have 7 minutes. Hold on. Oh, and that thing that happened again. I know the board is frozen. Hold on, I know. Okay. So for light, remember with sound waves, the frequency of a sound wave is interpreted by the, and I know the board is frozen, I'll unfroze it in a second, but remember with sound waves, the frequency of a sound wave is interpreted by the human brain as pitch or note, right? Similarly, okay, here comes back the board. Similarly, the frequency of a light wave is interpreted by the human brain as color. I'm just getting the board back. And I am aware of the time. Okay. For light waves, frequency is interpreted as color. So when light waves propagate from a star to us on Earth, and again, by the way, of course, I'll upload these notes. I know we have 5 minutes left. Of course, I'll upload these notes when we're done. And again, just try to catch, let this sink in when we're done. I'm saying it turns out when light waves propagate from a star through the magnetic and electric fields of outer space to us on Earth, what we find experimentally, empirically, what we find is that the color of the light as measured in Earth frame of reference, in Earth reference frame, tends to be redder, i.e. lower frequency, than as measured in the star frame of reference. Now, it's a whole discussion as to how we make that comparison, but suffice to say, we know from chemical composition of stars what the color should be or would be if it were measured according to the star, as measured in star reference frame. And then we measure directly in the Earth frame of reference. And what we tend to find with starlight in general is that the color as measured here tends to be lower frequency color, redder than it would be as measured from there, from the star. This is known as the redshift of starlight. The frequency seems to shift toward the red end of the spectrum as we compare measurements from there to here. So we say, aha, that makes sense. I mean, it wouldn't make sense, but it does make sense as long as we think of light as a wave. We say if light is a wave, then it is experiencing a Doppler effect. So if the frequency of the light according to us is lower than the frequency of light according to the stars, that must mean, in general, stars are spreading out from us, are moving away, right? If the frequency were higher, that would mean the stars were coming in toward us, but the frequency is lower than according to the stars. So the stars must be receding. Stars in general recede from Earth. And it turns out that they recede, and this is the last thing, they recede at a rate given by something called Hubble's law, as in the Hubble telescope. Stars recede at a velocity that is proportional to the distance away from us. Distance from us. This is the last thing I'm saying. Velocity of recede. And h is a constant known as Hubble's constant. It turns out that the farther away a star is, the faster it moves away from us. In general, we find, and how do we know? Because we look at the dot, we measure the redshifts of the light. So because of this whole thing, because we think we know how waves work, because waves are oscillations, because we have the electric field that is oscillating at a certain rate, we find that light is a propagation, a wave propagation through the electric field. Because waves obey a Doppler effect, when the frequencies of light as comes from stars to us, it turns out to be lower according to us than to the stars, we say, oh my God, the stars are moving away from us. We do calculations, Hubble does calculations, and we find that the farther stars are away from us, the faster they're moving away. So we get this idea that the universe is always expanding. This is where we get this idea that the universe, not just all the things in it, but the space and time of the universe itself is always expanding. And we run the film backwards in our mind and say, well, if the universe is always going like this, then if we run it backwards in our mind, that means that the universe originally was like this. That's where the idea of the Big Bang comes from. So the expanding universe idea comes from the red shift of starlight, which comes from the Doppler effect of waves, which comes from our belief that light is a wave, which comes from two-slit interference experiment of Thomas Young. And waves, we understand to act like a big bunch of like little masses on spring going back and forth all the time. But the weirdest thing about light waves is that the things going back and forth to create this propagation of this information we call light, the very thing that is vibrating back and forth to create the propagation of light is itself just bits of information. Light is an immaterial pulse through an immaterial medium known as electricity. That light gets redder as it comes to us from starlight, so we believe the universe is expanding. That is why we believe the universe is expanding. Do you have to believe that? No. You can believe whatever you want, but at least believe that we believe for reasons that are not arbitrary. That's the course. Do your best on the exam. I will. It'll be easier than it sounds. Just do your best. Just don't leave it blank. You've all been very, very good people, very patient people. I hope to see you down the line. I hope to support you in your future ambitions with recommendation letters or anything else like that. So please stay in touch and ask me. I will happily provide. And thank you. I will hang out if there's any questions or anything. I'll hang out for a second, but you're good to go. Have a great night and good luck next week.
Thank you so much, Professor.
Thank you very much. Thank you.
Thank you so much for being our professor this semester. It was truly an amazing experience. I feel like I learned a lot and you made physics very interesting.
You're very kind. You guys have been, you're very great. You are all great. This has been a lot of fun. I very much appreciate your kind words. And this would not be fun by myself. It is you guys that are fun. And you guys really have worked hard. I really appreciate it. And you've had a great attitude and been very patient. No, thank you guys. Oh, this is so, I'm gonna cry. Okay. No, you guys are awesome. I do hope to see you around, all of you. Also, I should really stop the recording before this gets upsetting. Okay. No, you guys are awesome. Okay.